and you can find me in the office C15 in the right wing of the cloister. Okay. Well, I am an astrophysicist, and I work on the evolution of solar type stars. Okay. Okay, this is the sun. So I think we all know that well, the sun is at this moment is stable, but it will be a time in which it will not be that stable. So stars evolve due to mechanisms that happen in their nuclei, and at the beginning, its changes will be slow and mild, but in the end, it will suffer a cataclysmic event that will eject part of its matter to the interstellar medium, enriching this environment. Okay. Now the star is right now in a group of stars that can be called the main sequence, in which all the stars are stable, but eventually it will go out from this stage and will become a red giant. In this stage, it will eject matter as a wind, and in the end, it will explode in the face of protoplanetary, planetary, what is it? Oh, wait, nebula. So all this matter will travel into the interstellar medium, enriching with processed matter and with mechanical energy that could destabilize parts of clouds that are quiet and but favoring the formation of stars like this that will eventually go into the main sequence again and so in an endless cycle. Okay. I'm not going to talk about all the changes that the nuclei undergo because it's out of the scope of this talk. But we are going to consider that the star I'm going to take as example will start to grow until reaching radii of the order of 2 astronomical units, and it will start to pulsate. Okay. In this moment, we can assume that this star has entered the asymptotic Gaia branch, or AGB. These kind of stars have temperatures of the order of 2,000 to 3,500 Kelvin, and they pulsate with periods of tens to hundreds of days. One of the main characteristics of these stars is that they are surrounded by a cloud made of gas that is expanding radially with velocities of the order of tens of kilometers per second. There is a theory that can explain, going to explain what we observe, and this theory says that the mechanism of the formation of these clouds are the following one. So the star pulsates and ejects a small fraction of matter from the atmosphere to a distance from the photosphere of more or less 1 stellar radius. Sorry. And in this, it's like it's forming a kind of extended atmosphere. This atmosphere is more or less quiescent. The gas is not moving; it's levitating. And but here the temperature is low enough to allow the formation of molecules in a gas that initially was in atomic form. Okay, part of these molecules are refractory and can condense onto dust grains. Okay. These dust grains are initially small, with sizes of tens of nanometers, and the radiation of the star is able to push them away like if they were a kind of a solar sail. In this travel, these grains meets cooler and cooler gas, and more refractory molecules stick to them. Okay. These grains grow and are accelerated by the radiation pressure of the star, and in the end, they act like a ball in a fluid and drag the surrounding gas. This is the way that in which we can move the gas from the star to outside. This process can be estimated the matter flux of this process and the mass loss rate of the star, and we can measure this quantity to have values of 10 to the minus 7 to 10 to the minus 4 solar masses per year. Okay. Regarding the materials that compose the dust grains, it depends on the chemistry of the star. An IGB star can be an oxygen-rich or a carbon-rich, depending on if the abundance of oxygen is higher than the abundance of carbon, or vice versa. For carbon oxygen-rich stars, the material that mostly compose the dust grains are silicates and metal oxides, whereas for carbon-rich stars, they are made of amorphous carbon and silicon carbide. Okay, we can calculate the mass the ratio of the mass in form of gas and to the mass in form of dust, and we get that it is about 300 in average. So this means that the amount of matter ejected from by these stars in form of a solid state form is quite small. But even if there is not, it is not very important. They are not very important in this sense. It is significantly important in for the citation, the kinematics, the thermodynamics, and the extent of the envelope of the gas component. Okay. Regarding chemistry, the circumstellar envelopes, which are the name that we give to this surrounding cloud, are stratified. Okay, here this is the star. Here, and here the matter is in the form of atoms, mostly atoms, hydrogen, helium, and small lower abundances of heavier chemical elements, and a few simple molecules such as dicarbon, the radical cyanide, or titanium oxide, for instance. And this is this region is comprise the inner layers of the envelope, and there we can find molecules which are non-reactive and neutral. The dust grains formed here, and these grains can move these molecules, which are called parent molecules, outwards. So during the journey in the inner layers and in the intermediate region of the envelope, they don't undergone important changes in their abundances, except for the case of the refractory molecules that can be removed from the gas phase. But when the parent molecules reach the outer layers of the envelope here, they meet the galactic UV ultraviolet radiation field, which is strong enough to dissociate part of them, producing radicals that can react with other molecules. So these radicals triggers a very active chemistry based on radical and radical neutral reactions, producing myriads of new molecules. In fact, most of the molecules detected in this kind of sources have been detected in this region. Beyond this region, it is supposed that all of the molecules are fully dissociated, and we only have atoms and dust grains. So the matter that enriches the interstellar medium are actually atomic and in solid state. Yeah. Well, when the stars approaches the end of the AGB phase, as I told you before, they undergone a cataclysmic event for which they eject half their mass, okay, in a big explosion or something similar. It's not an explosion from our point of view, but it's a fast process that takes only a few hundreds of years. During this process, the former star is replaced by a new one that is much hotter. So the temperature of these new stars can range from 5,000 to about 30,000 Kelvin. And the stars the hottest stars of this sample, of this group of stars, are able to produce a very strong ultraviolet radiation field that will interact with the neutral recently ejected matter, producing a very complex structure that can be resumed in this way. So we have the star, new star in the center, surrounded by a plasma, a fully ionized plasma, which is embedded in a photodissociation region. That could be, this is more or less this. And this photodissociation region is surrounded by the remnant of the circumstellar envelope developed during the AGB phase. Okay, this is something quite complex. Well, during this phase, these stars develop collimated high-velocity bipolar outflows, like in the case of this protoplanetary nebula, which is called M29. And these outflows change completely the shape of a large scale of these stars. We can have many examples with different shapes. Most of them are bipolar, but we have different outflows and have different shapes, square or something like that. So very beautiful, everything. Well, how can we observe all this? Okay, the simplest way is using telescopes, of course, single-dish telescopes like this in the picture. So these telescopes are mostly ground-based, like these telescopes here, and the IRTF. This is the Alto telescope in Spain. Telescopes in Spain. This the VLTs in Chile, and the 30-meter telescope in Granada. Okay. But part of these telescopes are launched to space, like in the case of the famous James Webb Space Telescope and the Hubble Space Telescope. And there is another class of telescopes that are in the middle. So it's a kind of hybrid telescopes like SOFIA, which are called the airborne telescopes, in which they put a telescope inside a plane. So it's very useful in some senses. Okay, but the single-dish telescopes can provide us with data easy to reduce and interpret, but they don't provide us with information about the spatial distribution of the brightness of the emission of the source that we observe. Well, it can be done for very big, very large sources, but in our case, in that study stars, it's not possible because the size of the stars are similar in size or smaller than the point spread function of the telescopes, which is of PSF, which is the size of the image of a point-like source. So we cannot get nothing from them. So we use interferometers. Interferometers works following the same principles as the Young double-slit experiment. So we take two different antennas, for instance, in the millimeter range, and observe one source and make their signals to interfere, okay, producing fringes. These fringes have information about the size of the source along the direction defined by the telescopes. Okay, so if we have an array with different pairs of telescopes, we can obtain information about the size of the source along different directions. It is possible with all this data to produce some kind of maps that could represent what we are observing. Well, what the PSF of single-dish telescopes are usually of the order of 1 to 100 arcseconds, depending on the wavelength that we observe. But with interferometer, we can reach resolutions, angular resolutions of the order of 10 to the minus 6 to 10 to the minus 5 arcseconds in the case of the very long baseline interferometry in which we use telescopes located in different parts of the Earth. So in the case of ALMA, that is an interferometer that we usually use, um, uh, the maximum angular resolution goes from 5 to 10 milliards. To put all this in context, we are going to say that the size of the AGB stars without the circumstellar envelope uh, ranges from 10 to 50 milliards in the case they are close to Earth. Okay. So it's possible to use interferometers to observe even the central star. Well, the output of these instruments are complex visibilities that are entirely related to the Fourier transform of the emission distribution in the sky. So we only have to invert these visibilities to get maps of these sources. Well, with all these instruments, we can observe in different ranges of the electromagnetic spectrum. All of them are important, interesting, but I am going to focus in three of them that I think they are the more interesting, at least for me. Okay. This is the millimeter, the infrared, and the optical ranges. So, well, the excitation, molecular excitation depends on several phenomena. The first one is rotation, in which the molecule rotates as a whole. The second one is the vibration, in which the atoms of the molecule vibrates inside the molecule. And the other one is, well, the electronic configuration, more or less, or the variations of the electronic configuration in which the electrons that make the atoms to be bounded change its configuration. So in this case, we have rotational transitions in which the molecule changes its way of rotating by emitting or absorbing a low energy photon. So one of the we have the spectrum of a molecule could be much more complex or simpler depending on the geometry of the molecule. We have a gas with different molecules with different abundances. We can have complex spectra like this one that is shown in this figure. But the rotational spectra of molecules have a very good characteristic for us, and it is that each molecule has a unique spectrum. So it is possible to use observer lines to identify molecules if we observe in the environment or the gas that we are observing in a sufficiently large spectral range. Okay, so with this kind of transitions, we can observe the corresponding lines and trace the whole envelope of AGB stars, because since they are slightly separated in terms of energy, we can detect changes involving very small, low temperatures, like in this case, that we can have here temperatures of about 50 Kelvin, for instance. The second type of transition is the infrared transition, and that is more or less the same as in the rotational case, with all the complexity of the rotational case, but we add here the movement of the atoms inside the molecule. So the spectrum is much more complex, and the photons involved in the process I usually observe in the infrared. In the other case, it was in the millimeter range. So all the lines here are usually grouped in form of bands. In this case, we have a band that is observed with a low spectral resolution, and this is the reason why we cannot have information about the individual lines. But if we had it, we will see something really, really complex. This is there is some pros and cons of infrared observations with respect to the rotational, the millimeter observations, and it is the following one. For instance, one of the most the worst things of this kind of data is that it is not possible to identify a molecule that produces a spectrum in the vibrational spectrum if we don't have enough spectral resolution, which is something that is really common, unfortunately. So this happens because all the molecules of a family vibrates more or less in the same way because they are very similar. So all the bands produced by all the molecules of this family are more or less at the same frequencies. So if we don't have a spectral resolution, we cannot study the individual lines, and it's not possible to say what molecule is producing that. But contrarily, it has some advantages. One of them is the fact that it is possible to observe the emission of molecules without a permanent dipole moment. It's something that is not possible to be done in the millimeter with rotational spectra because they don't have it. So this is we use this kind of spectra when we need something that can be given to us. So that rotational spectra cannot give us. And with this spectra, we can trace different, the inner and intermediate regions of the circumstellar envelopes. We can get some information about the outer region of the envelope, but in a limited way. And the last one are the electronic transitions. So they are similar to the vibrational transitions, but in this case, the upper and lower vibrational states are in different electronic states. Okay, so the spectrum here is really complex, and you have an example here with a low spectral resolution because it produces a lot of bands that are overlapped among them, and it is crazy. So interpret this kind of spectra is really difficult. But the transitions of these electronic transitions usually modify the configuration of the electronic configuration of the molecules by changing or moving the molecule from bounding states to anti-bounding states easily. This can have an impact on the reactivity of molecules, but we are not very interested on that point at this moment. And we are going to focus on what regions of the circumstellar envelopes we can trace with this kind of observations. And another advantage of these observations, of this spectrum, is the fact that we can observe with them diatomic homonuclear molecules, which are not available neither in the infrared nor in the millimeter range. So with these observations, with this spectra, we can trace the photosphere of the star and the inner layers of the circumstellar envelope. Again, as in the case of the infrared observations, we can get some kind of limited information about what is going on in the intermediate and outer shells of the envelope. And with all this introduction, I'm going to present a few examples to tell you what I have been doing during the last 20 years. So these are observations of one of the most important AGB stars in the sky. This is the carbon-rich star IRC 10216, or CW Leo, which is the same. And this is a sample of all the observations that we have. And these observations were taken with the 3.5 meters telescope of the Carrara Observatory and the high spectral resolution of the Carmenes spectrograph. So this is even in this sample, which is really small compared to the total, we can see a lot of lines of the carbon. If we take all these lines and refer each them to its rest frequency and arrange them, order them with respect to the energy of the lower level, we get this. Okay, Here we can study how the profiles change with energy. Uh, Here we can see how these lines present two different components. The one, this blue shifted component, which is only present in the low energy lines, and another component that is red shifted component, which is present in all the lines. With all these lines, we can do many things. Obtain, for instance, excitation temperatures for each component and the size of the line and the central frequency of each component to obtain information about what is happening in the envelopes. So in the case of the blue shifted component, which is narrow, the excitation temperature is of 50 Kelvin, and both the central frequencies and the width of the component are compatible with the terminal gas expansion velocity and the turbulence velocity of the gas in the outer shells of the envelope of this star. Okay. This was known since several years ago, but what I'm going to present you about the redshifted component, it is not. So in the case of the redshifted component, we derive excitation temperature of about compatible with the temperature of the star, and this temperature is the star is the only place in which we can get this temperature in this star. And this component is in absorption, so it is located between the star and us, and it is moving away from us because it is redshifted, and its width is really, really large. This means that the turbulence velocity is very, very strong. So putting everything together, we can deduce that we are witnessing some kind of matter infall on the star. There is another way of explaining all this, and could be, and it is that maybe we are watching how the star itself is shrinking during the last part of its pulsation cycle. So it is something very interesting because this is the first time that it's seen in this star, and I only seen something similar in another AGB star, so it's very difficult to get these results. Well, after that, I'm going to simplify the use of interferometry with this another star. This is a protoplanetary nebulae, one of the most important in the sky, also CRL 618. So in colors, you can see the emission of the H-alpha Barmer line mixed with atomic emission and continuum observed with the Hubble Space Telescope. So this is photometry, so we don't have information about velocities here. So, but we can get it with millimeter interferometry. So the contours in panels A, B, and C are represents the emission of the CO221 line at 1.3 millimeters, observed with ALMA. In these panels, I have plotted different velocity ranges and with different angular resolutions, and we can see how the correspondence between both images is very, very good. So we can, with this technique, assign velocities to the different structures that we are able to see with the Hubble Space Telescope. Panel C is a bit different. Here we can see very small the continuum emission of the ionized core or of this star, which is that region that was composed of plasma and was surrounded the central star. As you can see here, this star has these outflows, and this outflow to the left, the east, is blue shifted, is coming toward us, whereas this one is moving away from us. Going back to panel D, I'm going to tell you that this emission is not possible to be traced in the optical, because here you don't see anything, but what we have is a very optically thick dusty torus that prevents us to observe anything behind in the optical. So, but we can do it in the millimeter range. Well, we also used observed a recombination line, H30 alpha here, and that are formed also in the ionized region. This line is not contaminated by any other emission coming from any other place of this nebula. So here I'm showing you the total flux integrated over frequency, and we can see how there is here is not. I cannot see it very well. Here it's better seen in the screen, but as you can see here a kind of a structure that is we can define it as an incomplete ring-like structure that is inside the emitting region, and it is probably related to the stellar system that it should be inside this structure. This stellar system is thought to be a binary system, and this annular structure would be related in this case with the orbital movement of these stars. And in the lower panel, we have the average double velocity at different positions of the emitting region. And so we have here blue shifted emission, as I told you before, and red shifted emission. This is the foundations of the outflows. This is not very easy to observe. But here you can see a kind of whitish region, which corresponds to with the ring-like structure. So this is suggesting that the velocity expansion velocity field is really complex. Well, to the right, I'm going to I want to show you the emission of the HC3N 24 to 23 line in core scale. In this place, the blue and orange contours represents the limits of the CO2 to 1 emission that I showed you before, and the black contour in the center is here represents the limits of the ionized core. So you can see how the emission of this line of this molecule, sorry, comes from the neutral regions, which are here, and mostly from the boundaries of these regions where the UV radiation field are expected to be stronger. This is something that, well, we have other maps in which this is much better shown, but they are smaller. And this is what the chemical models predict to happen. And finally, I'm going to present one of the last works. This is ongoing, and I'm going to. I've been doing it with Alex and Pedro Carlos Gomez Calzada of the Complutense, and this is based with it. We try to find the spectrum of iron carbide. So molecules with iron are very difficult to observe to detect for any reason. We don't know exactly why. Only one molecule has been found in space to date. Has been iron cyanide. But 1 year ago, Coleman and Thuris found another 3 lines of another molecule, which is iron carbide, toward the GB star IRC 10-216. As I told you, it is not clear why these molecules are not present in gas phase, but it is probably because iron-bearing molecules are very refractory, and they probably condense onto gas grains in the very moment in which can do it. We started to work, and Alex calculated high-quality potential energy surfaces for this molecule, and Pedro calculated the spectrum of this molecule around 830 wave numbers, more or less. I had observations of this star at this wavelength, frequency, and we are trying to find lines here. So you can see that there are many features, weak features, that are apparently real. Most of them can be explained by reversional transitions of acetylene and hydrogen cyanide, but there are some features that cannot be explained with these molecules, and coincides with features of iron carbide. So we are not sure about this. Still, we have to explore the whole range. This is not the whole range. We have a larger spectral range, but this is promising. So maybe in the near future we can present a paper with this detection of this molecule that exists, but much closer to the star where they are expected to exist before it condenses onto that range. So I think it's time to finish. So thanks for your attention. I want to conclude saying that these kind of stars are very interesting, but there are a lot of work to do to understand the evolution of these stars and their impact in the galaxy. So we are going to use every instrument, spectral range, and everything to get data that could provide us with a complete view of what is happening here. So thank you.
Well, thank you, Pablo, for this very interesting talk. I don't know if there are some questions in the audience.
Just a curiosity,
Yeah.
what is FTWHD? Because for me,